So this is a presentation I actually prepared 2 years ago for a soil and groundwater remediation conference in Banff, and sort of tied it to a tailgating theme they had one evening. So it's not really in season right now. Football season hasn't started. It's still hockey playoffs, but hopefully there's some CFL or NFL fans in the room that might appreciate some of this. So the great Peyton Manning, who retired a couple of years ago, often used the cadence at the line of scrimmage where he'd say Omaha, and a lot of people had no clue what that meant. So after Super Bowl 50, when the Broncos won, one of the reporters asked him what he meant by Omaha, and so what he said was, it's Omaha is a run play, but it could be a pass play or a play action pass, depending on a couple of things: the wind, which way we're going, the quarter, and the jerseys that we're wearing. So I've sort of tied that into how we look at soil and groundwater remediation, because there's no two sites are the same. There's a lot of different variables and a lot of different conditions that you have to deal with every time, so it's always a unique situation. So our outline today, we're going to kind of follow a very basic sort of run through a typical football game sequence and sort of tie that into different elements of in-situ remediation of petroleum hydrocarbons. So we'll first get into the huddle and talk about some of the planning measures. Then we'll talk about a kickoff, an opening drive, and what that's all about. Then we'll look at the defensive side of the ball and how we deal with light non-aqueous phase liquids, which are also referred to as free product, and then the petroleum hydrocarbons that are dissolved into groundwater, and how we're going to, what type of technologies we have to contain those. And then we'll switch over to offense in a 1, 2, and 3 down scenario, where we target free product, which is usually your source impacts on petroleum sites, what's absorbed to the soil, what's dissolved in groundwater, and I'll quickly run through some of the typical remediation technologies that can be used in those situations. And then at that point, we're hopefully headed to the end zone and going to bring our site to closure. So in the huddle, some of the things we need to consider first of all is our field position. Where are we starting at? What is the client's remediation objective? It's very important that you understand that and have that conversation with them at the front end. Do they just want to control source? Do they want to just remove source? Do they want full remediation to a generic standard? And we want to determine what those endpoints are going to be for remediation. Then we want to look at the strength of the defense. And in remediation and situ remediation, that's really the geology and the permeability of the subsurface, because that's typically the first thing that really impedes progress from an in-situ remediation perspective. Then we'll look at our injury status, which is, do we have any financial limitations that the client might have? Are there other third-party stakeholders that may have a say in the matter, affected adjacent landowners? Maybe there's First Nation groups that need to be consulted or have some input. And then lastly, what's our clock management strategy? What are our deadlines to get this work done? What are some of the key milestones we want to hit along the way? So during the kickoff and opening drive, this is when we want to sit down and typically do a remedial options analysis. So we'll review the conceptual site model, which is all the phase 1, phase 2 environmental site assessment information. It was one of those boxes that Sean had in his presentation. So we want to really understand the conditions, the extent of the impacts, the characteristics of the hydrocarbons, look at any data gaps we might need to fill along the way, identify any potential limitations that might affect the technologies that we think have value here. So are there buildings over top of contamination? Is there infrastructure, underground utilities, pipelines in the way that we have to work around? We'll typically want to identify multiple technologies through this analysis process, look at the advantages and disadvantages of each, estimate costs on sort of an indicative high level. What are the capital expenditures the client's going to have to deal with? What are the ongoing operations and maintenance costs for them? And one thing that's often neglected at this early stage in the process is, what is it going to cost me at the back end to decommission the technology and the remediation system? At Matrix, we'll often take our clients through a scorecarding process where we'll look at different sustainable remediation metrics, environmental, economic, and social, and we'll just sort of weight them based on their business values and priorities, and that'll help screen out technologies that don't meet their values. And then we'll typically recommend one or more technologies. Sometimes, but not always, the regulator might require you submit a formal remedial action plan that really lays out what you're going to do, when you're going to do it, what commitments you're making, and how you're reporting on that. And then you might lead into the engineering phase where you're doing conceptual or detailed designs of remediation systems. So on the defensive side, there's a number of different ways that we can contain LNAPL or free product. So there's barrier walls and cutoff walls. So on the bottom right is an example of a permalock barrier wall, similar to a Waterloo barrier. It's just an interlocking wall that you excavate and place in the ground and put a hydrocarbon-resistant sealant between the grooves. On the picture above that is an example of a steel sheet piling that you would drive down into the ground. You can also use geosynthetic liners or slurry walls that can be a mixture of like a bentonite grout, cement, and maybe sand, and engineered clay where you can backfill and compact to a moisture and a compaction density standard. Basically, you're just trying to decrease the permeability to prevent ongoing migration of the free product. You can also do this through traditional excavation means with excavators, track hose, and then you'll see in the bottom left picture there, it's an example of a big beastly single pass trencher. I think there's only one or two in Canada right now and a few down in the US, but it's a way to do it without opening up massive excavations with big sidewalls. They're really neat machines. Then you want to look at how to collect the free product. So there's a number of different methods for free product skimming, downhole pumps that can be pneumatic or electrically driven, intrinsically safe ones, belt skimmers, floating skimmers that look like flying saucers that have hydrophobic filters and just let the free product drain in and then it hits a level switch and pumps out. Or you can use passive skimmers you manually install and remove, or absorbent socks. You can also go with traditional means of pump and treat where you're moving total fluids, but then you're having to separate the free phase, the free product LNAPL from the water above ground and treat the water and dispose of it. Or you can use suction pumps above ground like adductor pumps. For groundwater contaminants, so usually that plume is going to be further out than your LNAPL plume. You can install barrier walls to intercept that plume. So there's permeable reactive barriers, which are often a combination of sand and granular activated carbon. So as the hydrocarbons move through it, they'll adsorb to the carbon, and either the natural microbes will slowly degrade them, or you can also buy products off the shelf now, like Plume Stop by Regenesis, where they have bioaugmentation products or microbes already activated on the carbon with some macronutrients. And you can sort of do this as a continuous PRB, as you'll see in the top right A diagram, fully intersecting the plume, or you can use cutoff walls or low permeability barriers to funnel it into a central gate and get higher concentration material treated there. So now we're switching over to offense, and we're going to attack this free product that we have. And this is where we normally like to hit it with vacuum extractive type technologies, because they're quite aggressive. So we're just inducing a negative pressure on the subsurface. I won't go into a lot of detail here and bore you, but there's 3 or 4 different methods that you can use. Soil vapor extraction really just draws air and vapors out of the unsaturated zone, so above the free product and above the water, but it's good at stripping the free product. There's multi-phase extraction and dual-phase extraction, which are quite similar, but just little nuances of differences, where you're also pulling liquids, so hydrocarbons and contaminated groundwater, under a vacuum pump, and then treating it above ground and treating the emissions before you vent it to atmosphere. You can also do skimming and pump and treat, like I mentioned previously. So those are just a schematic on the right that shows sort of the basic fundamentals of how those different technologies work. So presumably once you've got all the source, the free phase out, you want to still deal with what's adsorbed to the soil particles. So again, some of those extractive techniques like soil vapor extraction and multi-phase are also quite effective for doing that. But there's other things like bioventing, where you can put vertical wells around the perimeter of your plume, open them up to atmosphere, put extraction wells in the middle, and basically you're drawing fresh air in across the plume, enhancing biodegradation, feeding oxygen to the natural microbes, the hydrocarbon degraders that may be down there. You can bio-augment as well. I think the jury's still out for some of us on how effective that really is versus the cost, and I know there's a lot of microbiologists that are concerned that, you know, introducing lab cultured species into the natural environment, they'll just be cannibalized. But I think some companies have had success for it, like the one at Sirens here in Ontario. Then there's in-situ thermal, where you're basically heating up the subsurface and you're volatilizing as much of the hydrocarbon as possible. The other benefit to in-situ thermal is that you're also creating a more conducive environment to the microbes. They're a lot happier when the soil and water temperatures are 20 to 50 degrees Celsius as opposed to 2 or 3 or 5. And then you can also look at doing fracking just to enhance flow. My opinion on that is it's more effective in consolidated materials like bedrocks and not so much in the unconsolidated or drift deposits. So then we're left dealing with what remains in the groundwater, dissolved into the groundwater. So in addition to using something like vapor extraction, you can air sparge, which is just a means of pushing air under pressure into the water phase and adding oxygen and bubbling it up to volatilize the hydrocarbons and kicking up the dissolved oxygen to enhance biodegradation. You can do traditional pump and treat here again, like I've explained earlier. Vacuum enhanced pumping, which is similar to dual phase and multi-phase. The thermal, and a couple of new ones I haven't talked about yet are in-situ chemical oxidation. So this is basically, you know, adding chemicals to treat chemicals, which isn't always the solution, but if you understand the stoichiometry, which I often don't, I'm not a chemist, it'll break down the hydrocarbons into carbon dioxide and water, and so it can be quite effective at polishing the last remaining dissolved phase you might have a site. And then you can also promote biodegradation by oxygenating the plume, so adding it using products like calcium peroxide and that sort of thing. Here's a couple of pictures on the right of an in-situ chemical oxidation program. They excavated the bulk of the contamination in the upper 3-4 meters, and then using direct push techniques on that skid steer backhoe, they injected hydrogen peroxide, and you can see a little bit of steam. I don't think my laser pointer will work from here, but you can see a little bit of steam coming out of the ground because there's a very exothermic reaction when you're dealing with hydrogen peroxide. So hopefully at this point you're within the red zone, which in football terms is the last 20 yards before you get to the end zone. Oftentimes you have to combine multiple technologies to get to your end goal here. There's very rarely is there any one single approach of in-situ remediation that will do it all for you. So you might be finding yourself at this point not quite getting to your endpoint criteria, where you've got sort of recalcitrant levels and yields from your systems, and you may need to rethink how you're going to finish things off here. You may have to give some consideration to doing a human health and ecological risk assessment, or making a case for a monitored natural attenuation process. But hopefully you're taking your site into what we'd call a retirement stage and putting it to closure. That's all I've got. Thank you for your time.